All right, this first section that I want to look at, exponential and logarithmic functions. This is a section really just to do some review with these two types of functions, just point out their main characteristics and things we're interested in as it pertains to things we're going to talk about in calculus. And really just for the simple fact that these two types of functions in the real world, in real world applications, naturally occurring situations, these two types of functions are everywhere. And so in our discussion of calculus, we're going to talk a lot and we're going to come across a lot of exponential and log functions. All right, so I just want to do a quick little review with you, touch on the main characteristics, main components of these two types of functions. What are they all about? How do they work? That kind of thing. So as we discuss them in our context or in the course of the calculus discussion, right, we have a better understanding of what these two types of functions are all about. Of course, we'll talk about polynomials and rationals and all of our basic types of functions, but you're going to see these quite a bit, and I tend to find that the students maybe don't have as much of an understanding about these two, especially log functions. I mean, we probably have a little better understanding of exponential functions just because of the basic exponential property of things, but probably not as much of an understanding as log functions. So just a quick review on these two types of functions and what they're all about so we can make use of that going forward. So we'll start with exponential functions. First of all, exponential functions, we're looking at functions of the form f of x equals a to the x. That's the basic format for an exponential function. We have a base raised to a power. And keeping in mind the difference between, say, an exponential function versus like a power function, like f of x equals x squared, for example, polynomial, but we also call that a power function. An exponential function has a base that's a constant, right? So the a value is a constant. The variable is in the exponent, as opposed to a power function like x squared, where the variable is in the base and the exponent is a constant. Right? So difference between exponential functions and our power functions. So f of x equals a to the x. A is our base. It's a constant. There are limitations on that base. The base has to be positive and not equal to 1, as defined for exponential functions. And the reason for that, just real quick, the positive nature, if you plug in, say, a negative base into an exponential function or have a negative base, that exponent can be any real number. Right? X is an element of the real numbers. And remember from your algebra, if you take a negative number and let's say raise it to the 1/2 power, for example, then that would be like this, what, the square root of a negative number. And remember, that's not a real number. Right? That's our imaginary number. That's where that whole complex number idea comes from. So to avoid the complex numbers, to avoid the imaginary numbers more specifically, the base of exponential function is restricted to be a positive value. That way you can raise it to any power and you're always going to get a real number. Not equal to 1 simply because if you take a number and raise it, or you take 1, excuse me, and raise it to any power. So if I have 1 to the x, I don't care what x is, you're always going to get a value of 1. And if you were to graph that function, that's just a constant function. You're going to get a horizontal line. So we restrict the base to be positive, not equal to 1. And you end up then with these two basic forms of exponential functions, or these two basic characteristics. If that base, if the a value is greater than 1, and you graph an exponential function whose base is greater than 1, say for example 2. You take 2 and raise it to larger and larger powers. That number is just going to get larger and larger, right? 2 to the first, 2 squared, 2 cubed, 2 to the fourth, etc. You're going to get values that are increasing in value. So if you take an exponential function whose base is greater than 1, you end up essentially with a graph that looks like this. And they're all going to have the same basic shape to their graph. I'm calling these basic exponential functions. I'm not doing any transformations and all that stuff with it. But again, just a basic idea of what these look like. So they're all going to basically look like this, regardless of what that base is. As long as the base is greater than 1, you get an increasing function. Notice the y-intercept. If you plug in 0, and this will be one of our basic properties of exponents. We'll review those here in a little bit. But if you take any number, well, any non-zero number, and raise it to the 0 power, you always get a value of 1. So I don't care what that base is, whatever a is, a to the 0 power, is always going to give you 1. So you get the same y-intercept for all of these basic exponential functions. They're all going to pass through the point 0, 1. The other side of that is if you have a base that's less than 1, say 1/2, for example. Now, if you take 1/2 and raise that to larger and larger powers, and I'm just talking integers, but remember those could be anything. X could be any real number. But let's say you take 1/2 and raise it to the first power, or 1/2 and square it, 1/2 cubed, 1/2 to the fourth. Right? Those are getting smaller and smaller. Right? 1/2, 1/4, 1/8, 1/16, etc., etc. You get values in this case that are decreasing. Right? So you get a decreasing function. So it's the basic characteristics of what exponential functions are, what they look like, what their graphs look like. Make sure we're familiar with the basic shape of the graph. That's always useful in dealing with functions. So whether the base is greater than 1 or less than 1, increasing function or decreasing function. Asymptotes, right? We always, we have asymptotes on graphs of functions. Exponential function, every exponential function has a horizontal asymptote. For the basic exponential function that we're talking about here, it's the x-axis, whose equation is y equals 0. Remember, asymptotes always have equations. If they're horizontal, as we have in this case, it's y equals. Vertical asymptotes have the equation x equals. The domain of every exponential function, and that actually just comes from our basic definition. We said x is an element of the real numbers, so that's your exponent. So we get the domain of every exponential function as a set of all real numbers. We always talk about domains of functions. Sometimes we mention the range. We always talk about the domain. The range of our exponential functions, and this is going to come from the fact that, look, you're raising a positive number to a power. I don't care what the base is, less than 1, greater than 1, what have you. If you take any positive number and raise it to a power, raise it to an exponent, you're always going to get a positive number. So for that reason, the range of the exponential functions is 0 to infinity. Again, basic exponential function prior to any type of transformation. So, being familiar with domain and range, that's always useful. Again, we're always interested in just the basic characteristics of these functions. What does their graph basically look like? Inputs and outputs, domain, range, that type of thing. Now, one exponential function in particular that we are interested in is what we call the natural exponential function. You may remember this number e. Number e is approximately 2.72. Now, this number e is a natural phenomenon. It's a number that occurs naturally, just in real-world situations. And there's a few different definitions or ways that we can come up with this number that we'll talk about in a second. But in terms of our exponential function, e can serve as the base of an exponential function. So I have f of x equals e to the x. We call it the natural exponential function. That number e is called the natural base. Right? And again, it's just because it's a naturally occurring phenomenon, a number that occurs in nature. And it happens to have a value of approximately 2.72. That's the value that we use for that. It's one of those decimals that never terminates and never repeats. So if you look at that, you go on your calculator and type the number e in, you're going to get one of those decimals that goes on and forever and ever and ever. It never terminates, it never repeats. It's an irrational number. All right, so our natural exponential function base e. We are very much interested in this function. This function is going to be your friend. We're going to see it a lot, and in the course of our discussion of topics involved in calculus, this natural exponential function f of x equals e to the x is a very, very friendly function when it comes to, say, finding derivatives and integrals and all the things that we're going to talk about. Now, this number e in particular, a couple of things I'm going to mention here that we're going to talk about as we get into chapter 2, which is where we're going to start our discussion of calculus. So we're going to expand on these couple of things that I'm going to talk about here, but just to give you an idea of the types of things that we're going to be interested in. The number e, one definition of it, is that it is the value of a with these exponential functions that we're talking about, such that the slope of the tangent line at the point where x equals 0 is exactly 1. Now save that idea for later. Now we're going to talk about tangent lines and exactly what the heck is a tangent line. All right, so we're going to have some discussion on that. But I'm looking at a line, essentially, that touches a curve, touches a graph, at a single point, but is in the direction of the curve. Right? So here's the tangent line. It touches at a single point, right, but it's in the same direction as that curve. So if you kind of take your pencil and you place it along that line, where I have that line drawn, and then move your pencil to trace the curve, and your pencil is forming a tangent line. So it touches the curve at exactly one point in the direction of the curve. Again, we're going to talk about that extensively because that's one of our main topics at the beginning of calculus. But it turns out that if you look at the exponential function f of x equals e to the x, our natural exponential function, it turns out that the slope of the tan line at the point 0, 1, at that y-intercept, is exactly 1. Now, it's like, okay, well, what's the big deal there? Well, yeah, great, it's 1. We're going to have a use for that. So, like I said, save this for later. That's going to come in handy for us down the road as we get into our discussions. And the fact that the slope of the tangent line at the point 0, 1 on the graph of f of x equals e to the x is 1. But again, we're going to have a lot more discussion about tangent lines coming up. Another place that this number appears is this in the discussion of when you look at values of limits. Now, when we get into the calculus part of things, there are three main parts to calculus that we're going to talk about, three main concepts. The first of which is a limit. Then we're going to talk about derivatives, and then we're going to talk about integrals. Those are the three main topics or parts of calculus. So the first thing that we'll start with is the idea of a limit. So when we get into chapter 2 and we start our discussion there, we will extensively talk about what a limit is, what are you describing, how do you evaluate limits, and all of that. So, but the main idea behind a limit is, here I'm looking at the limit as x approaches 0. So in other words, I'm looking at values of x that are getting closer and closer to 0. And if you take this expression, 1 plus x raised to the 1 over x, and you plug in values for x that are getting closer and closer to 0, you will see outputs that are getting closer and closer to approximately 2.72. That's number e. Now, so this is something you can do on your calculator. If you put this expression into your y equals editor, and then go to your table and plug in values for x that are getting smaller and smaller and smaller. And when we say getting close to 0, I would plug in numbers like 0.1, 0.01, 0.001, that kind of thing, and see what values you get out of this thing. And you're going to see pretty quickly that they're going to be approaching 2.72. It also happens with this next expression. If you take this expression, 1 plus 1 over x raised to the x, but in this case, you take x values that are getting larger as x approaches infinity, but you're going to get the same thing. You're going to see values coming out of this that are getting closer and closer and closer to 2.72. It's a really, really cool phenomenon. And they actually use those expressions. They actually get used in banking. That's a discussion for another class, but those are expressions that actually get used in real world applications. But there's our number e popping up. Now, this last thing I have for this part is just a reminder of some of our basic rules of exponents. Obviously, we're going to have to make use of those because what I find to be the issue in a lot of the discussion of calculus, it's not so much the calculus topics that cause the problem. It's a lot of your basic algebra, right? So you need to make sure that you're clear on your basic algebra, basic fundamentals there. That's why that's so important, because like I said, the concepts that we talk about in calculus, I don't think end up being very difficult concepts. Certainly they're going to be pretty straightforward as far as what we're measuring, but it's the execution of the problems, of the concepts, and a lot of that depends on basic algebra. So We're going to have to review basic algebra going forward, and that's always caution students, you know, yeah, you may have to make sure you understand the basic concepts of calculus, but that's not typically going to be the problem. Right? It's all of your basic algebra and trig, the couple of classes that you have to take before this, that cause most of the problems. So we'll review basic algebraic concepts going, as we go through and as those become necessary. So here, just reminding you some of our basic rules of exponents, and maybe to a certain degree, we're used to doing things a certain way in algebra, like when we multiply like bases, like I take a to the x times a to the y, or say like x squared times x cubed, and we simplify that to get x to the fifth. We add the exponents. Remember, that works both ways. So whether I have a product of like bases, a to the x times a to the y, and I can combine that by adding the exponents, it also works the other way. If I have something where, say for example, I have x raised to the x plus y, I can rewrite that as a to the x times a to the y. Right? So I can break it up in the opposite direction. So it works both ways. That equal sign is a two-way street. Similarly with division, right? But of course opposite in terms of the operation. We have our rule of exponents that says if I have a quotient involving like bases, a to the x divided by a to the y, I can simplify that by subtracting the exponents. So a to the x minus y, and vice versa. Right? Power raised to a power, right? That's where we multiply. But again, it works both ways. And you're going to see in some cases, we're going to take something that looks like this, and actually it'll be to our benefit to rewrite it this way. So when we're talking about, simplifying, rewriting expressions, which way you write it, it kind of depends upon the context. You'll hear me say that a lot in our discussions. It's all about context. What is it that I'm working on or intend to do with this particular expression? And that's going to dictate how I write it. So it may be useful in one form if I'm doing something with it. It may be useful to write it in a different form if I'm doing something different. So it's all about the context. But regardless, power to a power, right, we multiply the exponents. If we have a product raised to a power, we can apply that exponent to each factor individually. Remember, this also works for division. So if you had, say, a fraction a over b to the x, I could do the same thing, right? I could apply the exponent to each of those individually. And again, it works both ways. Now, that's not true for addition and subtraction. I'm going to write this because I don't know how many times we say this and we forget. If I have a sum, let's say a plus b raised to the x power, right? This is not equal to a to the x plus b to the x. Right? So say just something as simple as a plus b squared. That's not equal to a squared plus b squared. That's what I mean by that basic algebra. Remember, you have to multiply that out. So if I have a binomial or some sum or difference raised to a power, I have to multiply that thing out that many times. All right. So don't make this mistake. I see it done way too often, and it's a basic algebra mistake. This is what we mentioned earlier. Remember, we said that if we have a number raised to the 0 power, that's always going to equal 1. The exception to that is 0 to the 0 power. We're going to have a big discussion about this guy in chapter 4. Well, if you take 0 and raise it to the 0 power, what does that actually give you? And so that's a discussion for a later day. But otherwise, as long as the base is not 0, any non-zero number raised to the 0 power has a value of 1 by definition. The use of negative exponents. So remember, the negative exponent is a reciprocal, essentially, or can be written as a reciprocal. So if I have a base raised to a negative power, I can rewrite that as 1 over that base raised to the opposite, which would be positive in that case. But again, remember, it works both ways. So if you move a factor, that's the most general way to say it, moving a factor from the numerator to the denominator of a fraction or vice versa changes the exponent on that factor. Now, of course, again, provided a is not equal to 0, because that again could cause some issues with the value itself. I mean, we end up with undefined fraction if we have 0 as our base to some power, right? So typically that's going to give you 0. You end up with an undefined fraction. So we throw that in as well. We have our little restriction as always with denominators of fractions not being equal to 0. All right. All right, so that's our exponential functions and exponential type expressions, reminding you of those. Logarithmic functions, or just simply log functions. Now, I guess the main thing to remember before I talk about the log functions, when we come down here, exponential functions and log functions are inverse functions of each other. All right. Remember what an inverse function is. An inverse function essentially just undoes whatever a function does. So if I have a function like, say, f of x equals x squared, the inverse function would undo the squaring. And if you're going to undo a square, you would use your square root. Right? So f of x being the function x squared, its inverse function, f inverse of x, would be the square root of x. Right? So those are functions that undo each other. Well, that's what exponential and log functions are, and that's really where log functions come from. It comes from the idea that an exponential function has an inverse function. What is the inverse function of the exponential function? And that's where the log functions actually came from. They came from, trying to define the inverse of an exponential function. Now, the usefulness of that relationship is everything that you know about exponential functions can be used to help you understand log functions, because everything is just opposite. It's inverse, right? So whatever an exponential function is, the log function does exactly the opposite of that. So everything you talk about with an exponential function, it's just the opposite for a log function. All right, so the basic equation, a log function base a, we say this is f of x equals log base a of x, where notice the base here is still restricted the same as it was for the exponential function. Remember, it said the base of the exponential function had to be positive and not equal to 1. Same thing is true here for log functions. That's read as log base a of x. The base a has to be positive and not equal to 1. Here, though, notice x, we call that the argument of our log. It's restricted to be a positive value. More on that in just a second. But that's by definition. Graphically, again, depending upon the size of the base, if the base is greater than 1, just like with your exponential functions, you get an increasing function. So you get a graph whose basic shape is something like this. Now remember when we talked about the exponential functions, they all had the same y-intercept. Their y-intercept was at the point 0, 1. Notice for the log functions, their x-intercept is at the point 1, 0. Right, so in other words, log base a of 1, regardless of what the base is always going to produce a value of 0. So if your argument is 1, the value of the log is 0. I'm going to write that because that's one that actually pops up pretty regularly, as we will see. Log base a of 1, I don't care what the base is always going to give you 0. All right, so I'll mention something about that here in just a second. If your base happens to be less than 1, right, so for a less than 1, you get a decreasing function. Right? But again, notice the same x-intercept at the point 1, 0. Log functions have vertical asymptotes. Remember, exponential functions had horizontal asymptotes. Excuse me. Log functions have vertical asymptotes, and it ends up being the y-axis, whose equation is x equals 0. Now again, that's for the basic log function, right? Log f of x equals log base a of x, unless we have some type of transformation that would cause that graph to shift left or right. Excuse me. All right, domain and range. Now here I'm going to be a little more careful about the domain, because remember with our exponential functions, the domain was a set of all real numbers, so not such a big deal. But with log functions, and that goes back to what we just said up here, We said that argument had to be greater than 0, so we have a domain of 0 to infinity. The range is all real numbers. Right? But like I said, we're typically more interested in the domain than we are the range, but there's our domain and range for the log function. Now, another way you can remember this or look at it is, remember this relationship between the log functions and the exponential functions. They are inverse functions. And one key relationship you may remember between inverse functions is their domains and ranges are reversed. All right, so, when we look at the function f of x equals a to the x, right, we plug in a value for x and we get an output, whatever that value is. If you take that output and you plug it into the log function, the inverse of that function, then that log function undoes whatever the exponential function did, and you're going to get back the original input. So essentially what happens then is x and y, your inputs and outputs, are reversed. Well, the inputs, those are our domain values, right? And the outputs, those are our range values. So a simple way to look at that is for inverse functions, we say that the domain and range are reversed. So whatever the domain and range are for exponential functions, the domain and range for log functions just get reversed from that. So if we go back to our exponential function, remember the domain was all real numbers? Well, that's the range of our log function. The domain of the range of the exponential function, remember, was 0 to infinity. Matches up with the domain of our log function, right? But of course, this is the main thing to remember here, because we are usually a lot more interested in, we always have to be aware of what the domain values are for a particular function. We need to know what those inputs are. So for a log function, the argument must be positive. Okay. What else? Yeah, that's good on that. Now, here's another very important relationship. And this we use for a lot as well, just to help us understand what the heck a log is. These two expressions, or these two equations, I should say, are equivalent to each other. To say that y equals log base a of x means exactly the same thing as saying that x equals a to the y. Now notice x here is your argument. That's the x here. Y here is the value of the log, corresponds to this exponent. And the base is the base. Right? The base of the log, the base of the exponent, all that's the same. Okay. Get all this out of my way. But the basic idea is this. Look, the value of a log is equal to the exponent that you would place on this base to produce the argument. Okay? So it's just taking the 3 pieces of the equation and rearranging them, and you have 2 equivalent equations. Right? So the one on the left, obviously, we'll call it the log equation. The one on the right, we call the exponential equation. But those are equivalent in their meaning. So when you're trying to evaluate a log, you say, okay, what's the value of log base a of x? It would be whatever the exponent would be that you would place on the base to give you the x value, to give you the argument. Right? But those 2 equations, the fact that they're equivalent to each other, and really remember, if you go back even up to this one, right, to say that log base a of 1 equals 0, remember the value of the log is the exponent that you would place on that base to produce the argument. And we've said earlier with our basic rules of exponents, any non-zero number raised to the 0 power always has a value of 1. Right? So keep that in mind when you're dealing with logs, helping you understand what the heck we mean by a log, or what the value of a log is. But we also have some other uses for this little conversion or equivalent relationship. Now, in dealing with log functions, when we talked about the exponential function, we said we're very much interested in that natural exponential function, base e. That's not exclusively the only exponential function you run across typically, but it is one of the more common. And for calculus, it's very important. Now, for log functions, in the real world, in general, I would say 99.99% of every log function that you ever come across in a real world application situation involves one of two bases, either base E or base 10. Right? There's that number E again, right? That natural base, that natural exponential function, f of x equals e to the x. Here we have the natural log function, f of x equals log base e of x. You never see it written that way. You always see it this way. All right, so that ln of x, that is log function base e. The other is the common log, we call it. It's base 10. But again, you never see it written with a base 10. You always see it written as just log of x. Those are the two buttons that you have on your calculator. You have an ln button. You have a log button. That represents your natural log function and your common log function. Now, in calculus, just as with the exponential functions, we are very much interested in this log function base e. So you're going to see a lot of natural log functions, a lot of ln of x. We're going to see the log base 10 pop up a little bit, the common log function. But most of the time, you're going to deal with your natural log function. Now, again, I said about 99.99, or how many nines you want to put on that, and real-world applications involve one of these two bases. You may see a little bit of base 2 that pops up, like in computer programming, that kind of thing, engineering. They'll see a little bit of base 2 stuff. But that's pretty much it. You typically don't see logs with other bases appear in real-world applications, just naturally occurring situations. It just doesn't happen. Right? So you can have exponential functions with any base, but you typically only see log functions with base E or base 10, for the most part. Now, I've also included this little change of base formula. So should you happen to run across a log with a different base and you need to do something with it. Now, on the calculators today, this depends on your calculator. I think most of us probably have this on our calculator. If you hit your math button on your calculator and you scroll down to the letter A, it'll say log base. And if you select log base, and it'll pop up either back to your home screen or your Y equals editor, wherever you're putting this in, you'll have a place then to put in the different base and the argument of your log. Right? If you would happen to have an older operating system on your calculator, it may not have that option, right? But otherwise, that should be an option. If you don't have that option on your calculator, or if you just don't care to use it, most of the time I don't even bother. You have to hit the math button, and then you have to scroll down to the letter A, and then you put all that stuff in. Another way that you could put in a log of a different base, should you ever have the need to do that, is to use this change of base formula. Log base A of x is equal to log of x divided by log of a. Or in other words, log base A of x is equal to the log of the argument divided by the log of the base. You could either do it with the common log, or you could do it with the natural log, ln of x over ln of a. So you could use either one of those, as long as you use the same one in both cases, right? And so that way, you're just using those buttons on the calculator. So we call it the change of base formula. You could take any log of any base and rewrite it that way. But again, for our purposes, you're probably not going to have a use for that, but if that ever pops up in some other context, to where you need to deal with a different base on a log, you could either hit that math button, scroll down to that log base option, or you could use this change of base formula. A few properties of logs, though, to remind you of. Now, these we actually do make use of on occasion when we're dealing with log equations. The properties that allow us to take either multiple logs and combine them into a single log, or vice versa. Take a single log and express it in terms of multiple logs. But as always, it's a matter of context in terms of which form of this is more useful in a given situation. So call these basic properties of logs as properties of ways that we can rewrite log expressions, log equations. If I have a log of a product, number one, so notice my argument is the product of x times y, I can rewrite that log as the sum of log base a of x plus log base a of y. So in other words, we say the log of a product is equal to the sum of the logs. Conversely to that, the log of a quotient. All right, here's log base a of x over y, where the argument is a quotient. That is equivalent to saying log base a of x minus log base a of y. All right. This third property, call it a power property if you wish, log base a of an argument that involves an exponent. Right, so I have an x to the p power. Can be written as p times log base a of x. In other words, I can take the exponent on my argument and place it in front of the log, and I have the product of that exponent times log base a of the base. We have uses for these, right, in different situations, primarily dealing with solving equations for the most part. So we're going to see these pop up on occasion. Right? Yeah, so basic properties of law. So I'll remind you of those as necessary, but yeah, you should have, I guess, seen those somewhere along the way. Now, one place that we do make use of those, and the other one that we talked about was the conversion, remember, between that exponential equation and that log equation that we said were equivalent to each other. When you're solving equations involving exponential or logarithmic type expressions, then that's where a lot of those properties and relationships come into play, come in useful, right, for helping us solve equations. So first, just an example, and again, as this becomes necessary later on, much later, then I'll remind you of how these work. But just to give you a little refresher and remind us of how we go about solving basic exponential and log equations at this point. So first, a basic exponential equation. I'm looking at solving the equation e raised to the 4x plus 1 power equals 17. And again, a pretty basic, nothing too involved here. But notice the issue when solving an equation like this, the variable's in the exponent. So I need to solve this thing for x. How do I get the variable out of the exponent? Well, that's where that conversion between the exponential and log equation can come in handy. All right, so this is what we had mentioned earlier. I can rewrite this by saying that that exponent, 4x plus 1, is equal to the log base e. Right, the base of the exponential, base of the log is the same, and that's our ln, right, natural log, base e. And then 17 becomes the argument of my log. So it's just a matter of converting from exponential form to log form. Now, this is just one way that this can be done. Before anybody has a meltdown, there are different ways that this can be done. This is just one way. Right? So for a basic function, or a basic equation, I should say, that's one way that we could solve this, is just by rewriting it. Because now I've got the exponent out of the base. Now we're just going to solve this normally. All right, so 4x plus 1 equals natural log of 17. I can subtract 1, divide by 4, and now I've got x equals natural log of 17 minus 1 all over 4. And that would be the exact solution to this equation. We're always going to keep in mind this as well. Do I need to find an exact solution versus an approximate solution? And so typically, if we're just solving an equation, we're usually interested in exact solutions as much as possible. If, however, this is, in the context of, say, an application where I'm trying to actually answer a question, then it would make more sense to go ahead and approximate that value, right? Plug it into the calculator and do an approximation. So just be aware of that. I mean, we're typically interested in exact solutions, unless we're in an application situation where I actually want to use that to answer a question. And it makes more sense to round it off, give a decimal approximation. But be aware of that. What am I asked for? Do I want an exact or do I want an approximate solution? An example with a log equation. And this is also an example of where we can use one of those properties that we just mentioned. So notice here, I've got natural log of x plus natural log of x plus 5 equals 3. First thing I did here, notice, was to combine those logs into a single log. And again, one thing I didn't mention when I mentioned that earlier was, that happened, or that can be done as long as the bases on the logs are the same, right? So in other words, if I have two different bases there, then that property would not hold true. And then that's not an issue. It's not anything we're going to have to deal with, but just for completeness. All right, so I do have the same base there I can combine, and that was our property that said the sum of logs can be written as the log of a product. Right? So natural log of x plus natural log of x plus 5 can be written as equivalently natural log of x times x plus 5 equals 3. And then I just rewrote that, distributed the x, so natural log of x squared plus 5x equals 3. And then I did the conversion. All right, so just like with the previous one where we converted from the exponential to the log, here the variable, notice, is located in the argument of the log. If I'm going to solve the equation, I have to get that variable out of the argument. And so one way that we can do that is to convert the log equation to its equivalent exponential equation. Right? So the argument, x squared plus 5x, is equal to the base of the log, which is base e in this case, raised to the third power. Now, continuing from here, I got rid of the log. I still have to solve the equation. Notice this is a quadratic equation. Now, keep in mind, don't forget this, that's a number. Right? E is just a number. E is a constant. It's not a variable. So anytime I see e or e to a power pop up, that's a constant. So I can treat that just like we would, the number 3 or the number 5 or the number 10 or what have you. And I can rewrite this as x squared plus 5x minus e cubed equals 0, which is how we typically solve quadratic equations. Right? So it's always in play when you're solving any type of equation. You have to recognize the type of equation that you have and what processes or steps you would take to solve that type of equation. And so one way that we can solve a quadratic equation is to use quadratic formula. All right, so we always have to keep that one in mind. Our opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's what I did here. I just plugged that into our quadratic formula. It just so happens that c is negative e cubed. And yeah, that's fine. We just plug those in. Now, we do have two solutions there, right? Because of that plus or minus, I've got two solutions. I've got negative 5 plus that square root. I've got negative 5 minus that square root. Now, on the negative side, so if I do negative 5 minus that square root, and I just did the approximations over here, you can plug those into the calculator and check that if you wish. The negative side of that gives me negative 7.6318. I just rounded it off to a few decimal places. And that's typical for log values. Rounding them off to 3 or 4 decimal places is typical. The positive side of that, the negative 5 plus the square root, gives you approximately 2.6318. Now, this is one additional issue that you do have to keep in mind when you're solving a log equation, and it goes back to the domain issue. Remember when we talked about the log functions, we said the domain, or in general, the argument has to be positive. So because, and you see this type of thing happen with some types of equations. We ended up solving this equation, right? A quadratic equation. The original equation, though, was a log equation. Right? And so because we used that conversion from the log to the exponential form, we eliminated the log from the equation to a certain degree. You still have to keep in mind, though, the limitations on the argument of the log. So once you solve your equation, if the original equation was a log equation, you need to check your solutions to make sure that they are valid with respect to the original equation. And for log equations, it's really just a matter of checking to make sure the arguments remain positive. So obviously in this case, I cannot use negative 7.6318 as a solution, because that would give me a negative log, a negative argument there. It would also give me a negative argument here as well, right? So otherwise, it would be a valid solution. I mean, yeah, you could plug it in and make sure you do get a true statement when you do that. Right. So in this case, we do reject this solution. The only valid solution is 2.6318. But, it's like we say with any equation. When you solve an equation, you always want to check your solutions. We say that. How often we do that, But just keep that in mind with any log equations. Make sure that whatever your solutions are ultimately, you go back and check to make sure that your arguments do remain positive. Right, so just a couple of examples, exponential log equations. We'll review those some more later as that becomes necessary. I just wanted to touch base with that. I also just went ahead and threw this in as well, talk about mention our trig functions, inverse trig functions. Again, probably not as big of a deal for us here in Calc 1. Trying to think if we end up solving any trig equations here, but definitely in Calc 2. If you're heading into Calc 2, we tend to have to deal with a lot more trig in Calc 2 than we do Calc 1. I mean, we'll talk about the trig functions in Calc 1, in the context of finding derivatives and antiderivatives. But you'll see a lot more work with your trig functions in Calc 2 if you're heading in that direction. But just to remind you, when you talk about a trig function, say y equals sine of x, remember x, your input, we typically think of that as an angle. Ultimately, they're real numbers, though. I mean, remember from trig, we ultimately end up talking about radian measure, and how radian measure of an angle is more useful because those are real number values. In calculus, everything that we do involving trig functions is done using radian measure. We don't use degrees for anything, right, in terms of calculations. So you should set your calculator to radian mode, and you shouldn't have any reason to change that when we're dealing with any of our trig functions, right? So make sure that's set appropriately. But for a trig function, when we think of the input, the x as an angle, right? But ultimately it is a real number. And then you get an output, and that's whatever the function value is. We call it a ratio. In this case, the y value is my sine ratio. But again, it's a real number. But just remember then for your inverse function, right? Because what we said earlier, the inverse function just reverses whatever the function does. The inputs and outputs change orientation, right? The domain and range get reversed. Now that's a whole nother discussion. If you remember from trig, you had to have a whole big discussion about domains of inverse trig functions and all of that. But that again, we'll refresh on that kind of stuff as it becomes necessary, if it becomes necessary. I'm just mainly interested in this whole inverse relationship at this point. But for an inverse trig function, that means that the input would be the sine ratio, right? And the output is the angle, quote unquote. Right? But again, ultimately, that is a real number as well. But we tend to think of inverse trig functions as, the output would be the angle, the y value is the angle, whose sine is x. Right? So just a little reminder there. But like I said, probably not as big a deal here in Calc 1 as it will be in Calc 2. But, just kind of touching base with these topics. And as they come up, we'll get into more detail with them and review as necessary. Okay. All right, that's it for this little section.